have a few in the textbook like this. I don't think anything on web work like this shows up, but because it showed up in the textbook, I decided to put an example like this into this. I have two separate absolute value groupings here, which makes it even more complicated because that whole process of me clearing the absolute value symbol gets a little bit more tricky. Again, though, I am going to use the definition of what an absolute value does, and I'm going to make some um, comments here about what we notice or we should notice about this problem. Well, first of all, there's a book problem similar to this. We do not know if x minus 4 or x plus 3 are positive or negative. Okay? It really depends on what x is. I mean, if x is like negative 7, they're both negative. If x, however, is more like negative 2, then x minus 4 would be negative, x plus 3 would be positive. If x is like 7, then both of these would be positive. So those are all possibilities. Either one's negative, both are negative, or neither of them are negative. And that's what I'm going to work with because that's what's important here. Because absolute values only affect whether or not a given quantity could be positive or negative, and if it's negative, I make it positive. That's essentially what it does. Even though I don't know what x is, or x minus 4, or x plus 3, I can definitely say that x minus 4 is less than x plus 3, because even though I do not know what x is going to be itself. Okay? And it's a very simple thing to take for granted. And if I subtract 4 from some given number, and I add 3 to some given number, that same original number, then obviously I'm going to have less overall by subtracting 4 from it than I am adding 3 to it. So we can make this determination and actually eliminate one of the possible combinations of positive and negative that we could possibly have for these values. So I'm going to have three cases here. Option 1 is that both x minus 4 and x plus 3 are negative, which means less than 0. So essentially, x is going to be less than 4 and at the same time less than negative 3, so overall x is going to be less than negative 3. Because if I'm less than negative 3, I'm automatically less than 4. Okay? So that's kind of like get into an idea of domain here. Under those circumstances, since x minus 4 and x plus 3 are both negative values, the absolute value would, if I was utilizing that, it's just going to perform the opposite of what x minus 4 and x plus 3 are. So when I clear the absolute value symbols of the original equation, I end up with a negative x minus 4 plus a negative x plus 3 equals 13. I do some simplifying. Subtract 1 from both sides, divide by negative 2. I get x equals negative 6. And there has to be some agreement between our premise and our answer. X equaling negative 6 is certainly less than negative 3, so the premise we worked under as well as the answer we got agree with each other, so it seems to be an acceptable answer. Option 2 is that I have x minus 4 being negative, because it is the smaller of the two, and x plus 3 being positive, because it's the bigger of the two. That means either x is less than 4 and x is greater than negative 3, or x is between those two values. So with that in mind, when I go through the rest of the problem, when I clear the absolute value from the x minus 4, since x minus 4 is still being treated as negative, I'm going to do the opposite of x minus 4. Whereas the x plus 3, if I'm treating that as positive, the absolute values would just drop out and do absolutely nothing to the x plus 3. So I distribute the negative. I combine like terms. I get 7 equals 13, which means there's no solution to this because 7 doesn't equal 13. So this option really would not be able to happen and have a situation where I would have those two absolute values equal 13. So it's just not going to work. But I do have my third option, and that both x minus 4 and x plus 3 are positive, which means that x is greater than 4 and x is greater than negative 3, which means overall that x is just greater than 4. So with that being the case, and both x minus 4 and x plus 3 being positive, when I clear the absolute values away from them, really nothing happens. Except some simplifying on both sides. X plus x minus 4 plus 3 becomes 2x minus 1 equals 13. I add 1 to both sides as well as divide by 2, and I get x equals 7. And those would be the two solutions to your equation. Sometimes equations like this can actually have an interval for answers. Very rare, but it can. But those are two answers, those are two values that if I put them in for x, I am going to get a positive 13 for my absolute value. So, or the sum of my absolute values. So, an inequality. An inequality like this, if you're using methods that you learned at high school, could take you a couple pages worth of notebook paper to do. The reason being is, first of all, we have an absolute value along with an inequality. And that means you have to go into all this stuff about ands and ors, and this or that. Which one is it? I don't know. Um, and so, that leads itself to some complications, sometimes make a problem last longer than it needs to be. Along with that, this is also a rational function, which means I have x's in the denominator. And one of the things we typically do is to get rid of the denominator part because we don't like having variables down there when we're trying to solve an equation. The problem is if I'm multiplying both sides of an inequality by anything that will help me deal with the x minus 1 down there, which means it's going to probably involve a variable, when I multiply both sides of an inequality by a number, if both sides are being multiplied by a positive number, the inequality sign would stay where it is. If you're multiplying both sides by a negative, it's going to switch, the inequality symbol around to the opposite sign. And that's, other scenarios you have to try out as you go through the problem, and that's why you end up solving, two cases, which each one has 4 cases to look at, and you're looking at a bunch of different scenarios that just don't work out. So there is a method that we use that we start going over more at the college level, which probably would have made your life a whole lot easier at the high school level, because at the high school level, when you deal with inequalities, they often do ask you to draw a number line, but it's more or less an afterthought. It's like, okay, after you find out what the answer is, plot the solution on a number line. Well, if you actually reverse that process and use the information you got to come up with the number line, then the inequality you need to have as an answer comes directly from that, and any ands and ors that might need to be a part of it will come naturally from that as well. Because if I have gaps, that usually indicates I have an or. If I have 2 segments, that have an endpoint on my number line, that's usually the result of an and statement. So this one here, what I'm going to do first is I'm going to write this as an equation first. I'm going to also make note that x cannot equal 1, because if x were to equal 1, that would put 0 in the denominator, and zeros in denominators of fractions are a big no-no because it gives us what we call an undefined value. We actually talk more about that as we get into limits and things towards the end of the course. So I'm going to write a similar equation. I'm now going to get rid of the absolute values. Same way as before. Here, because I have an equation. So I'm just going to solve the equation. So I'm going to multiply both sides of both equations by x minus 1. Didn't want to do that. There we go. So on the left I have 2x plus 3 equaling 5x minus 5, and I have 2x plus 3 on the right equaling negative 5x plus 5. So I simplify. Subtracted 5x from both sides of the left-hand equation, as well as subtracted 3 from both sides. I also, on the right-hand side, trying to see here. Yeah, I added 5x to both sides and subtracted 3 from both sides. And so what I get as answers here to the equation, the important part is the equation, is x equals 8/3 or x equals 2/7. Now, a mistake that a lot of students make is they would stop here. But the fact of the matter is, if you are given an inequality to solve, 99.99% of the time, the answer is going to be an inequality or an interval that you need to provide. It's just not going to be two numbers and that's it. Those two numbers are needed because they're going to help me define some boundaries on my number line, which I'm going to create up here. I'm going to put the 8/3 and the 2/7 on there because they're x values where I could equal 5, and I don't want to equal 5. I want to be on one particular side of it, greater than. I'm also going to mark the x not equal to 1 because of the fact that rational functions, they can jump from being, above a value to below a value, without having to actually become that value in between. It's like saying, okay, if I have a function, I'm here at y values of 10, I'm trying to find out where y values are 3, and I see that I go down as low as y values equal -4. It's like, well, then it has to go through and be -3 somewhere. Well, not necessarily if it's a rational function. And that's why I have to put the domain restriction in there. So I'm going to plot them where they belong, 2/7, 1 and 8/3. And what this does, and they're all open dots. The reason why I'm using open dots yet is because I don't know where I'm going to shade yet to know which way to orient the brackets and parentheses and so forth. However, I'm going to use open dots, and what these open dots are doing are dividing my number line essentially into 4 different regions. So what I'm going to do is I'm going to pick a number from each one of these regions. And I'm showing that right here. From the far left region, I'm picking 0 because it's less than 2/7. I'm picking 1/2 because it's between 2/7 and 1. I picked the number 2 because it's between 1 and 8/3. And I'm picking 3 because it's more than 8/3. And what I'm going to do is I'm going to test each one of these in the original inequality. If it makes the inequality true, then I'm going to shade that part of the number line because that number worked, which means every other number in that region is going to work. And if it doesn't work, I'm not going to shade that region. So when I test them all out, here's what I get. 0 creates a statement that's not true, so it doesn't work. 1/2 creates a statement that is true, so it does. The same thing happens with 2. And with 3, again, I get a situation that doesn't work, which means that, okay, the regions where I have the 1/2 and the 2, they're going to get shaded. I'm going to keep the open dot there. I could put parentheses at the ends of where the 2/7 and 8/3 are, but not necessary. This gives me an indication of what my final answer is. And I usually write them in interval notation because, as I said, from the number line, the interval notation is a more direct translation. So what I have here is x going from 2/7 to 1, a gap at 1 being 1 itself, and then 1 to 8/3, parentheses all around because I'm not equaling any of these. That union symbol, that U you see down there, stands for, is another way of writing an or. Usually we get interval notation, we start using a union and interval and intersection symbols, and you're going to see more of those momentarily.